Here are solutions to homework set number 11 for ECE 111, Intro to ECE. This homework set looks at inductors and the wave equation. Now last week we looked at capacitors. Capacitors are integrators. The voltage is the integral of the current. Inductors, in contrast, are differentiators. The voltage is the derivative of current. So the first problem is, suppose I have an inductor, say it's 1 Henry. If I specify the current, find the voltage. Well, the voltage for inductors is L di dt. If L is 1, it's just the derivative. So basically this problem is just asking you, what is the derivative of current? Well, derivative is slope. It says the change in y or change in x. So here the slope is 0. Y changes by 0 in 1 second. So the derivative is 0. There's the voltage. Here the derivative is minus 3. Y changes by minus 3 in 1 second. Jumps down to minus 3. Jumps back to 0. This is what we call a delta function. The slope is infinity, and it changes by 3. So what we do in electrical is symbolize that with an arrow. That's a delta function with a height of 3. That's kind of like a really tall, thin rectangle. Stretches to infinity with an area of 3. Then go back to 0. Here the slope changes by 4 in 3 seconds, so it's 4/3. So it's a little bit more than 1. Here's the negative delta. It goes down 4 in 0 time. So that's a delta, the height of minus 4. Back to 0. Another delta function. This has a height of 1. Another delta, negative, height of minus 1. Like that. So that would be the current or the voltage across the inductor. A thing to note with inductors, the current is continuous. The voltage can have a jump discontinuity. For inductors, energy is current. The current has to stay continuous unless the energy suddenly changes. The voltage can change suddenly, though. Voltage is not energy. Okay, problem 2 says, what happens if I have this 4-stage or this RLC circuit? What are the differential equations that describe it? Now, to simulate this, you need to come up with the differential equations that describe the circuit. Now, most of the people in 111 haven't had differential equations yet, but that's not a problem. We're going to use Matlab to solve. To actually solve by hand, stay tuned until you take, I think, math differential equations or signals and systems. Here, just the important part is get the differential equations right. Once you get the differential equations, Matlab can solve. Now, there's a couple ways to do this. What seems to work best for this one is a little bit tricky. First, I'm going to start with conservation of current. The current to the capacitor is the current to the node. That's IA plus IB plus IR. IC is C dB dt. That's the basic equation for capacitor. The voltage across the inductor is L di dt. So these are the basic equations. Now I want to combine them for the circuit. If I solve for IC, conservation current says IC is IA plus IB plus IR. IC is C dB dt. I'm using prime notation to indicate derivative. That's IA plus IB. IR is the voltage through the resistor, 0 minus V1 over R. Okay, now here's the trick. I want to find or substitute, but I don't know IA. I know the derivative of IA. So take the derivative of this equation. I get the second derivative, C dV double prime, is the derivative of IA plus derivative of IB minus 1 over R, derivative of V1. Now I can substitute. That goes in for IA prime. This goes in for IB prime. Substitute. Now solve for the second derivative and simplify. So dividing through by C, separating all the different terms, grouping all the terms together, gives you 1 over LC times V0, and minus 1 minus 2 over LC times V1, plus 1 over LC times V2, minus 1 over RC times V1 prime. By symmetry, all the nodes will be the same. So this is node 1. Node 2 is the same, just change the indices. 3 is the same, change the indices. So nodes 2, 3, and 4 are the same equation, just change the indices. The last node is a little bit different. with the last node, what happens is there is no current from the right. So this goes away at node 4. So this goes away, that goes away, this goes away, that goes away. So we just have 1 over LC. So the last node is just 1 over LC per V4 rather than 2 over LC. We plug in numbers. Here's the differential equations that describe that circuit. So it's a little bit of algebra, a little bit tricky, but writing the differential equations isn't that bad. Now this is where the power of Matlab comes in. To solve, that's actually a pretty hard problem to solve. Using numerical methods, it's actually pretty easy. What I do in Matlab is, given the voltage and its derivative, I can then calculate the second derivative. So here with my notation, the 2V is the second derivative, dV is the first derivative, and V is just voltage. I've got to use a variable that Matlab doesn't, or Matlab will accept. V prime is not valid in Matlab. Matlab prime means transpose. So here's the differential equation at node 1, node 2, node 3, node 4. Once I calculate the second derivative, integrate, I get the first derivative. Integrate the first derivative, I get voltage. Now plot the voltage as time goes by, and here's what it looks like. So here's the script. I'm going to run for 9.99 seconds. Here's my integration step size, 0.01. I'm going to let this puppy run. My V0 is 10 volts. I'm going to start at 0. Here's what happens to the voltage. Now notice last week we looked at RC circuits. RC circuits satisfy the heat equation. This satisfies the wave equation. The wave equation are coupled second-order differential equations. These behave very different. They just bounce around. On the homework, it's kind of hard to print out animation. So if I just plot the voltages versus time, here's time in second, voltages, that's what they're doing. Okay, it just bounces around. That's how the heat equation behaves. Very, very different than the heat equation. That's how the wave equation behaves. Okay, so going back, the reason it's called the wave equation is if I expand this to 30 nodes, you can see what's happening. What I could do is take the previous equations and copy 30 times. That's perfectly valid. This is where for loops are nice. I can put this in a for loop. The first node is about the same. I'll define these to be vectors, 30 by 1 vector, so I don't have to just use the index. I don't need 30 copies of the variable. Between nodes 2 and 29, just take at the ith node, go I minus 1, I plus 1. These all stay the same. And the last node. So this handles all of them. Matlab hates the index 0, so I can't do a v of 0. Matlab will hate that. But I can have a variable called v0. And here's the last node. Last node's a little bit different. Instead of being 30, it's minus 15 because there's only one inductor attached. This would be for 30 nodes. And this part right here is just kind of a little snap like that. Makes it easier to see the wave equation or simulate it. So going back over here, here are my differential equations. I'll integrate acceleration to get velocity, integrate velocity to get position, and let's run this for 12 seconds. So here's what that looks like. This is why that's called the wave equation. When I snap it, I launch a wave and it travels down the transmission line. When it's the right endpoint, I get a thing called reflection. Now, if the right endpoint is really, really loose, this number is really, really small, I get a plus reflection. It came in with an amplitude of 1, it reflected, and came back with an amplitude of about 1. If I change that to be something smaller, so this is problem number 4, I think. If I make this number small, meaning that last resistor on the far right is really large, I launch a wave. The right endpoint moves freely, and I get a plus reflection. Now, plus reflections are bad. This isn't part of the homework, but kind of illustrates nicely what's going on. But let this run for a while. 22 seconds. When I get plus reflections, I get a thing called standing waves. So suppose this is the wind blowing, this is a bridge, something satisfies the wave equation, or a circuit board trace where I'm sending sine waves going back and forth. With the reflections, I get these standing waves. That causes bridges to collapse. That causes the voltage to go over voltage on my circuit, breaking components. Those reflections are bad. Suppose instead of making this last term really, really small, I made it really, really big. What that means is that last node, go over here. At the very last node, I take that resistor and make it really, really small. So 1 over RC is 100. Now what happens, let's just run this for 12 seconds and see what happens. If I make the last term really large, meaning R is really small, notice the right endpoint just barely moves. So there's just barely moving. That really stiff causes a negative reflection. Now negative reflections are also bad. I go back over here, let this run for 22 seconds. Again, this is a part of the homework. It kind of illustrates why these are bad. If I had a circuit and I send the signal down it going plus minus 0.5, if I have a negative reflection, the right endpoint just barely moves. I've got a negative wave coming back, another wave going forward. I get these standing waves, just like I had before. Now the input used to be 0.5. The standing waves have an amplitude of 1 already. That large voltage can break components. The last problem says, what is the Goldilocks number? So right here, 100 was too big. 0.01 is too small. Let's try a number like 1. See what happens. Now when you take electromagnetics, you can actually calculate what resistance to want to place at the end to stop the reflections. If you haven't had 351, not a big deal. Just do trial and error. And try different numbers. 100 is too big, 0.01 is too small. Here at 1, I still have a plus reflection. 1 is too small. Let's try 10. If this last number is 10, that's 1 over RC at the endpoint. Notice the right endpoint, it moves, but not as much as before. I get a minus reflection. So 1 is too small, 10 is too big. Let's try 5. Launch a wave. And this is where Matlab really shines. If you haven't had electromagnetics, I don't really know how to calculate that. That's okay. I can simulate in Matlab and see what happens. This is still slightly negative on the reflection. Let's try 4. The actual number is the square root of 15. But using trial and error, I can get pretty close. So we hit the right wall. That's pretty close to 0. So I would say 4. Significance is if I get rid of reflections, I get rid of standing waves. So now, if this is a transmission line, I'm at radio broadcast, I'm setting a signal down. Instead of getting these reflections, which cause standing waves, all the reflections are gone. And without any reflections, I no longer have standing waves. So that is homework set number 11 for ECE 111. With inductors and capacitors, I get second-order differential equations. You can set it up so it satisfies the wave equation. The wave equation occurs over and over again in nature, similar to the heat equation, but the two are very different. Heat equation last week behaves pretty well, it just warms up, cools down. Charge capacitor, discharge a capacitor. Wave equation is very different. Wave equations tend to make things bounce up and down and oscillate. If you have a system described by the wave equation, it's actually a lot harder to control. And that's relevant to electrical computer engineering because we see that all the time as well. That's homework set number 11 for ECE 111. And one other thing, this is part of the beauty of Matlab. I've got a fairly complicated system. I actually have a 60th order differential equation that describes this, 30 nodes, each one second order. With Matlab, I can solve using numerical methods. by using numerical integration, even if they haven't had Calc 4 differential equations or 351 electromagnetics, I can still solve using Matlab. Matlab is a really powerful tool. Again, homework set 11 for ECE 111.